Well, thank you all for coming late in the afternoon instead of drinking pisco sours. But we'll get there. It's been a great conference for me. I've learned really a lot. I come into this from the paleontology side, which means I think about years into the past and lately years into the future as a result of that. And to learn as much as I have about what's going on here on the ground in the conservation world has really been inspiring and stimulating. And one of the things that comes out is that there's a lot of places in the Amazon and on the planet that are under threat. And, you know, we worry about losing ecosystems, we worry about local impacts, and ultimately one of the reasons we're so worried about that is because we know that those human pressures oftentimes lead to extinctions. And of course, not just in the Amazon. So I think that it was Ken Feely a couple of years ago, 2009, had a paper in PNAS, excuse me, about projected plant extinctions in the Amazon, and I've forgotten the exact numbers, but there's Ken, so maybe he remembers 5 to 9% are at risk of loss by 2050 for vertebrate species. There was a study by Ewing and Science in 2012, which pointed out that somewhere on the order of 38 to 55 vertebrate species would probably be gone by 2050 if we did nothing differently. And this is all, those are all based, or the cause of those are primarily land transformation, okay? Now what's driving that land transformation? I think my role here today is to kind of step back and look at the global pressures that are actually driving what's going on the ground, and to think about how do we actually address those. And I think that's very important to think about because there have been numerous studies done, and this happens to be one that was picked up widely last summer in June. Gerardo Ceballos and Paul Ehrlich and myself and a couple of other co-authors, where we pointed out that even using the most conservative assumptions about rate of species loss, we could be looking at 75% of species going extinct within the next couple of human lifetimes, okay? Now think about that. You go outside and look around, and 3 out of 4 of the species that are familiar to you would be gone. Okay, that's what we in the paleontological world call a mass extinction. And that's really what I want to talk about here is how plausible is it that we're headed for one of these mass extinctions? And to get at that, we have to think about how we compare present and past extinction rates. So that's the first thing I'll do. And then I want to think about what are these big global drivers that ultimately we have to get a handle on if we're going to tackle this crisis. And then third, the question everybody's interested in is, can we avoid it? Is it inevitable, or can we do anything about it? And you know, I will answer that last question right now and say I am guardedly optimistic, but we got a lot of work to do, and I'll tell you why. So the 6th mass extinction, why do we call it that? Well, as someone who works with the fossil record, clear documentation that there are 5 times in the history of complex life, that is over the past 550 million years, when extinction rates elevated so much that in a geologically short period of time, we lost at least 75% of the familiar species on Earth. And this chart up on the board simply shows you that. When they were, there's the name of the geologic time periods, don't worry about that. When they took place, one of them took place 443 million years ago. That's what the MA stands for. another one 359 million years, and so on. The one we all know about is the dinosaur extinction. That took place about 66 million years ago. The one I want to focus you in on is the Permian. Is there a pointer up here? Yes. Is the Permian extinction 252 million years ago. 96% of the known species disappeared during that one. And that, as best as can be dated, took place within 60,000 years, probably much shorter than that, but due to the vagaries of dating rocks, it's hard to pin it down anymore. So the thing about these is they were all caused by we'll say natural phenomena, okay? Major changes to planetary orbits or to plate tectonics, moving continents around, or major volcanoes, or in the case of an asteroid, or in the case of the dinosaurs, an asteroid coming out of the sky and striking the Earth. Well, today, we've got a cause that we actually can do something about, and we have the fortunate situation of being able to see what's coming if we look hard enough. So we know that we kill species, okay? Over the past few centuries, we humans collectively have wiped at least 900 species off the face of the Earth. We know we did that. We also know, or are pretty sure anyway, that we have killed about half of the vertebrate wildlife in just the past 40 years. And when I say killed half of the wildlife, I mean we have reduced population sizes of many species by about 50% or more, reduced their geographic range size, so those animals just aren't as common as they used to be by a long shot. We also know from efforts by the IUCN that we've got at least, I think the number is now about 28,000 species of those that have been assessed that are known to be at risk of extinction. So that's the magnitude of what we know has happened over the past couple of centuries. Now, in order to figure out whether that's unusual at all, we have to think about background rates of extinction. And, just like people are born and die, that's a natural phenomenon, okay? And we can calculate a normal death rate in a population of humans. What's unusual is if we have a bad epidemic or something and wipes out a whole bunch of people at once. All right, so that's sort of the difference between a background extinction rate and a mass extinction rate. And if you take a look at this animation that just ran through, what you see is as you go through time from 600 million years ago on to the present, you have species bouncing around in this interval. That's the background extinction rate. That's normal, okay? But then you have these 5 times that are statistically far above the background rate. Those are the mass extinctions. And then the big question now is, where do we fall in terms of going into the 6th mass extinction? All right, so to do that, we have to think about how we're measuring extinction rates, how we define a background rate, and so on. So the rate metric that is a very good one to use was actually put out there by Stewart a few years ago. It's called extinctions per million species years. And I'll explain in a little bit more detail in a minute what that means, but just remember that's the rate metric we're using for now. Calculating current rates relies on looking at the IUCN classifications of species as to extinction risk, and then comparing it to a background rate. There's a lot of different ways to get a background rate. Usually, the rates that people have used are something like 0.1 to 1.0 extinctions per million species years, and those are based on some kind of back-of-the-envelope paleontological data that was put out there in the 1990s, and recently Stewart and Lucas, and I can't remember who else is on that paper, if anybody, calculated background rates of crown groups using molecular phylogenies, excuse me. Now there's another way to get at extinction rates, and there's also something else to think about. When you're comparing fossil data with modern data, or long time periods with short time periods, it can be very much like comparing apples and oranges. Really, the only way that the two data sets taken as a whole are similar is that we know very little with respect to the entire spectrum of species that either are alive or ever lived in the past. If we're looking at the current record, the IUCN data, we know something about 4% of named species. And there's a bunch of species out there that are not even named. If you look at the fossil data, it's less than that even. It's probably 1% or less. So first take-home lesson when you're comparing rates and talking about a mass extinction, we're talking, if we're talking scientifically, we're talking about what I will call familiar species, okay? The species that are either, that we like well enough in the modern landscape to go out there and sample in census or have time to sample in census, and the species that happen to be preserved in the fossil record because they're abundant. But I would actually argue that the biases that are taken as a whole are kind of a wash. And the thing to remember is we're dealing with a subset of familiar species when we're talking about mass extinctions. All right, this is the way they really differ, though. Got several problems you have to overcome if you're going to make this comparison. So there's timescale problems. As I'll show you later, there's issues with comparing a short, what goes on over a short interval of time, i.e. centuries, with a long interval of time, that is millions of years. We talk about defining species and doing, species extinctions, but there's lots of different ways to define a species. And it turns out that if you're looking at the modern record these days, most of the species that you're talking about are actually defined using molecular data, DNA divergence data, or some other related technique. Whereas if you're talking about fossils, typically you're defining species by what you can do with the hard anatomy. Counting species. So in the modern record, you can count species, but oftentimes people will count populations, which are subsets of species. In contrast, in the fossil record, what people tend to count most often are genera at the genus level. And then what ecosystems are sampled in the modern record, we know most about species that live on land. In the fossil record, we know most about species that lived in the sea. And those species are primarily clams and snails and things like that. And then the geographic coverage, we know roughly the geographic range all over Earth of the species that we assess for extinction in the modern record. Fossil record is much more spotty. You have a few localized geographic regions that tend to produce a temporally very long record. So there's one way around this if you want to use the real empirical data, and that is to use a group in the fossil record and modern record that has good data and is comparable. And that happens to be mammals for a variety of reasons. But with mammals, you can read the table there, but basically we can go all the way from the short durations of modern mammals and get enough overlap with the fossil record to take things back deeply in time. So we get around that problem. It turns out that in mammals, species defined at the molecular level are by and large not too different from the species one defines at the morphological level, so a nice match there. Mammal fossil record is actually good enough to work with species and sometimes even populations, and ecosystems they come from are very similar, and the coverage is still not anywhere near as good in the fossil record as it is with the modern record, but it's not too bad. So here, for example, are all the fossil localities that have this particular small ground squirrel in North America, and the blue dots are multiple localities in one place. So we literally have millions of fossil specimens that we can identify to species. So a very good sample size. Okay, now the other thing that's important to remember when you're calculating background rates from fossil data is just really where that data comes from. So here's where it comes from. It comes from the rocks, okay? And paleontologists go out to exposures like this, and they walk around and they smile, and they say, boy, I'm happy to be in the field. And then they say, hey, look, I found a fossil. And get out their tools and their paintbrushes and, expose everything. Pack it up so you can put it on a truck or something, because those are about 300-pound casks, and then take it back to the lab, okay? So you do that and throughout that whole cliff sequence, and what you end up with is something like this. But I'm going to take you from the field to how an entry actually gets in the database. First, you find your fossils. Then you have to have a way of dating your fossils, because you can't put a number of years on fossils themselves. You associate them with a radiometric date that you typically get from a volcanic ash. So in this case, we have an ash at that dates out to about 30 million years, 28.7, 27.5, and so on, up to 16 million years old. So now we've established a chronology. Now we can see where each of our fossils falls in that chronology. And for any particular species, you can determine the lowest occurrence, how many million years ago it first appeared, and how many million years ago it last appeared in a given local sequence, okay? And then you do that for the next species. So you do it for multiple species. And what you end up with at any local area is a chart that looks like that, and you can see some species are short-lived, others are long-lived, and then you go to the next rock exposure. Now, geology isn't kind to us usually. You might have one set of exposures in this geographic area, another one in this one, but it covers a different amount of time, so you match it up by beds you can trace. Go on to the next one, do the same thing, and so on, until you end up with a composite section of a very long period of time that basically for mammals we have this sort of record that spans about 66 million years, and it's been pretty well worked out and dated. Okay, so the mammal fossil record comes from literally hundreds of rock exposures, hundreds of paleontologists working over hundreds of years collecting fossils. It's resulted in millions of specimens, and we study those to the extent that you can identify about 12,000 fossil species. There's about 5,500 modern species, okay? Now, as I say, all that's been now compiled in fossil databases. You can mine that data out, and by the way, if you just Google the paleobiology database or the Neotoma paleoecology database or FaunMap or MyoMap or NeoMap, all of this stuff is on the web to download. You can play with it. Modern data, as I said, comes from the IUCN. And what we end up with then is determining background rates from that fossil data and the time resolution on that as we go from 66 million years ago on up to essentially the present, is you can bend that, depending on where you are in the time scale, to anywhere between 1 million and 100 years. And then as you get nearer and nearer to time, you can actually get it down to tens of years. And then with historical records, of course, down to the year. So there's the background rates. And then the current rates, we look at what went extinct over the past 500 years. And then we can play games like say, okay, what if all the threatened species actually went extinct over the next 100 years? What would those rates look like? So we can project into the future as well. Now there's one other nuance here that you need to take into account. I told you that we're talking about extinctions per million species years, and all that really means is that if you have 1 million species there, how many are going to go extinct out of that million in a year? Okay, so an EMSY of 1 means that 1 species out of every million should disappear every year, okay? Now, as for actually calculating that, here's the nuance. Just pretend that's a section of rock, and those lines are the first and last occurrences of the species that are found in that fossil record. And the orange blobs are times of extinction. So all you have to do is you count up all the species that go through that sequence for a given time interval. And let's just look at this time interval, 100,000 years, okay? We count up 10 species, 3 went extinct. Things are mathematically equivalent to just taking that proportion extinct, which is 0.3, 3 divided by 10, divide that by time, 100,000 years, multiply that by 1 million years, and there's your EMSI, 3 in this case, all right? Now here's the nuance. Longer time intervals will statistically give you a very high probability of getting a lower extinction rate than a short time interval will. And basically, you know, that makes sense if you think about it. If you thought about doing a rate of temperature change as you go from the heat of the day to the coldest part of the night and dividing that by 24 hours, that's going to give you a much higher rate than if you took the rate of temperature change as measured from summer to winter, okay? Because there's a lot of variability that you pick up when you measure short intervals. Okay, so like in this case, if we just looked at that interval, we get an EMSY of 3, and if you look at the whole thing, the million-year interval, you get a 1 of less than 1. So bottom line there is you have to statistically adjust for that, okay? All right, so we've actually done that. And what comes out from the empirical mammal data is the background rate is actually pretty close to 2. Now, what does that really mean for extinction today? There are 5,500 mammal species, give or take, on the planet, or there, and have been for the past couple of centuries. Each circle on this slide represents a mammal species, and there are 5,500 dots on there. Count them. So we can ask ourselves, how many species would we expect to go extinct in a century under a background rate of about 2 species per million lost per year? And the answer is 1, okay? That's what we'd expect. What do we actually see? 43. All right, so that right there tells you that with mammals, we're at least 43 times too high. Now, another way to look at that is to ask, if we were at that background rate of about 2 extinctions per million species per year, how long would it take for us to have observed, under that background rate, how long would it take for 43 species to go extinct? There's your answer, about 3,000 years. We've done in a century what should take 3,000 years to do. And you can see for the other vertebrate groups, again, using the mammal background rate, it's about in that same ballpark. These are using less conservative assumptions here. But the bottom line here is that's a very, very conservative assessment of our modern extinction crisis because it uses a maximally high background rate and also a minimally low modern rate. There's various assumptions that go into that. So this is the best case scenario, okay? And under that best case scenario, we can then say, all right, what happens if we go into the next 100 years and we don't do something and we lose most of those threatened species? Again, for mammals, that pumps our rate up to over 1,000, okay? We don't want that to happen. Even with the rate we're seeing now, if that kept going, a mass extinction, that is a loss of 75% of familiar mammals, in this case, well, actually, of all vertebrate species, and all of the species that are listed in these groups, could take place within 2 to 3 human lifetimes if you run out the math using linear assumptions. This is just a little extinction amometer, 0% extinct here, 100% extinct here. Here's the big 5 mass extinctions, the 75% benchmark for a mass extinction, and then these are the percentages for threatened species in each of these groups. So that's the bad news, okay? That's kind of where we stand. All right, now here's the good news. As far as species that have actually disappeared off the planet, less than 1% in most groups. What that means is we still have almost everything out there that we want to save, everything we've ridden the planet with for the last 12,000 years. So, what do we have to think about if we're going to save those species? There's a few givens here, and the big given is we live in a rapidly changing world. Since 1950, about a half century ago, the world has witnessed more change in more dimensions than it has in all of human history, and I would argue in much of the history of complex life. And here's why. Starts with how many people there are on the planet, and each of those people needs something to eat, a way to make money, and so on. That leads to habitat loss, which we've heard a lot about at this conference. It leads to making money off of nature in ways that are not renewable. Those things both feed into extinction. And recently, as Ken so nicely pointed out this morning, is we also are causing a lot of global climate change through our need for energy. And I'll talk about that in a little bit more detail. But I think as we go into the future, as conservation biologists, the first thing we have to remember is there will be 3 billion more people in the world by 2050, all right? So we have to figure out how to make this work with 3 billion more people in the world. And these are just various projections of what population growth could do by 2100, based on different assumptions about fertility rate. And I think you can probably ignore this one, okay? I don't think we're going to get to 27 billion people. I don't think the planet can sustain that. However, if we brought down fertility rates to replacement rate in countries where that isn't already the case, That's the blue line, and that pumps us up to stabilizing at about a little over 10 billion. If fertility rates are just a half child higher than that, we get up to 16 billion. If we actually got to half child below replacement rate, we begin to drop and stabilize around 7 billion. But the thing to notice is it doesn't really matter too much which of those scenarios. By 2050, we're somewhere between 9.5 to 11 billion or 10 billion. All right, so we're going to be there, and that's a problem for other species because right now, with 7 billion people on the planet, there are way too many big animals. And what I mean by that is if you take all the animals on the planet that weigh over 100 pounds, those are megafauna, all right? We're megafauna on average. Some of us weigh less than 100 pounds. But the human species is megafauna. You can actually do a calculation, an estimation that traces the biomass of megafauna back hundreds of thousands to millions of years. And this is the normal megafauna biomass that the planet can support. And I'll tell you why that is in a minute too. However, humans now are that much more, and the domestic livestock that we have are that much more, okay? Here's the biomass of all the wild animals on Earth. So what that means is if we're going to keep 7 billion people alive, we got to grow a lot of food. And we're already using almost, it's a little over 40% of the planet for food production, but if you add in everything else like roads and dams and cities, we've taken over 51% of the planet's land. All right, so lesson number one, we got to feed that 3 billion by 2050 by not taking over any more wild lands if we want to keep species alive. All right, it's the bad news. The good news is actually the food security people have run the numbers, and it's possible to do this by doing some things differently. I don't want to dwell on that. I'm happy to answer questions. The other thing, of course, is all those people have to have a place to live, money to buy a place to live, to eat, and so on. And, you know, before we had 7 billion people on the planet, we could kind of regard nature as this bottomless checking account that we could just keep drawing on. Now there's too many of us drawing on it, okay? So the well is running dry. Everything from, you know, deforestation issues to gold mining on the Rio Madre de Dios, and pollution problems to outright hunting species because you can make money. So that's my categorization of the drivers of extinction then are the food, money, and then the one I want to spend the most time talking about is the power issue, because that leads us into climate change, which I think is a really underappreciated problem. By power, I mean the energy it takes both to run the global ecosystem and to live the style of life we've become accustomed to. Okay, we're all biologists. We know that ultimately, before people got into the act, the entire global ecosystem had a set energy budget, which was the bottleneck of photosynthesis, converting sunlight heat energy into chemical energy by plants. Things eat the plants, animals eat the plants and other animals, and that amount of energy is 728 exajoules, give or take, on land. All right? That's how much there is to work with from photosynthesis, and how much there has been for hundreds of thousands of years. Okay, now people, we now co-opt about 30% of that, so we take 211 exajoules, give or take. That's out of the picture for other species to use, but that's actually not enough for us. Look at this number. In 1 year, we consume around 760 exajoules of energy. That's the whole global society, which is more than what photosynthesis can produce for the whole planet. And you know where we get the rest. We use fossil photosynthesis, essentially, fossil fuels, which, of course, is having the problem of heating up the planet. And this is where we get into the problem for other species and extinction. And, you know, when I give talks on climate change, almost always, if I give them to a non-academic audience, the question is, gosh, it's only, you know, 2 or 3, even 4 degrees. What's the big deal? That's not so much. Well, here's the big deal. We're going from 600 million years ago to the present. And this is an estimation of how temperature has fluctuated throughout the history of complex life. And if you look at that temperature scale, we go a little less than 10 degrees C. 10 degrees is the thermal fluctuation of the planet over 600 million years. We're cranking it up, if we stay with business as usual, by over half that amount within 200 years. That's the big deal, and that's why species have trouble responding. If you crank up, if you warm the planet 4 to 6 degrees, a lot of tropical forests are going to go from that to that. All right, and as Ken showed us, species can't move that fast and they can't adapt that fast. In the oceans, it's not only warming, but ocean acidification. Basically, if we kept going at present rates, by 2070, there's a good chance there would be no more coral reefs on Earth, which boils down to 25% of the ocean species, right? That's within many of our lifetimes. People have recently tried to quantify the amount of added risk from climate change, and it's substantial, even with the relatively limited data we can get our hands on. But this was a paper in Science by Urban that basically used, it was a meta-analysis that pulled together a lot of other papers. But what I want you to look at are these orange bars are all of the species we know to be at risk from causes other than climate change. The red bar is the species we now think are going to be at risk from climate change. And if you stack the red bar on top of the orange bar, and especially if you add in this outside probability, what you end up doing is increasing the number of species at risk of extinction by about 50%, okay? And this is a different study that takes into account some other things, not only species distribution modeling, which was most of the data for urban study, but also some species interactions and some species physiology. And it looks even worse when you do that. So basic story is climate change has the potential to really put things over the edge. Now, it also has some sort of even scarier possibilities. This is a study done by Jack Williams and a couple of his colleagues a few years ago, but it's one that blew me away when I looked at it. Now, when we think of climate change, we tend to think of temperature change, and when we think of temperature change, we know that closer to the poles are experiencing more temperature change than the tropics are. However, what Jack and his colleagues did in this model is to not say, let's look at temperature change. They said, let's look at how the combinations of climatic factors, precipitation, season length, temperature, let's put all those together, let's see how those will change. And then let's scale that by the amount of annual change that species in a given region are actually adapted or have evolved to withstand. And of course, that It's a whole different way of looking at it because the tropics have been pretty stable, okay? Well, what comes out with that is they basically said under the worst case IPCC model that you would have a lot of places on Earth that had climate change in such a way that those climates just aren't on Earth anywhere today, all right? So those are novel climates. And in contrast, a lot of the places that species depend upon today would have the climate and combination of parameters they depend upon disappear altogether. Now, the thing to look at is that red is bad, okay? Red's always bad on these maps. And look at where the red is concentrated. It's in the most highly biodiverse areas, including this area. So, who knows what will happen with that? And if you really want to lose sleep, you can start thinking about lessons from the deep time fossil record. This is why I told you to remember the Permian. What we now think caused that Permian extinction, 96% of all the familiar species dropping out, is about 6 degrees C of global warming caused by rapid injection of CO2 into the atmosphere, in this case by volcanoes that covered most of Siberia, and ocean acidification, all right? So when I put all that together, I say, boy, I really want to stop climate change. And, you know, I think this is a really underappreciated thing. If we want to avoid the sixth mass extinction, absolutely all the things we're doing are essential. We got to keep at them because, you know, it's on the ground where it all takes place. But we also have to address these global drivers. So how do we do that? You know, it's not easy. But what you probably might not know, and what a lot of people have just thrown up their hands in despair and said, we can't do it. We actually can, and we know how to do it. And I'm using the example of climate change, but this actually applies to the money and food parts too, which I don't have time to talk about. But the first thing is to sort of really think about what has to be done, okay? And with climate change, yeah, it's a global problem, but the richest 1 billion people in the world, which include, you know, I would venture to say most of us sitting in the room fall in that category, contribute 60% of greenhouse gases. So that's lesson number one, or two or three, I've lost count of my lessons, that it's sort of a top billion problem. Contrast, the poorest 3 billion people contribute only about 5% of greenhouse gases. So how do we fix it? The issue is we have to bring down what that top 1 billion is using and bring up what the bottom 1 billion has available for energy without increasing greenhouse gases. Well, we actually do know how to do that. People have cranked the numbers. This particular study did the numbers, and by 2030, we actually could convert the entire world to carbon neutral energy by building this number of machines, okay? And they're big numbers. You can read them off, I'm not going to. And you look at those numbers and say, wow, we can't do that. That's a lot of work. But now think about what we've done over the past, well, from 1950 to the year 2000. We dammed 60% of the world's large rivers. We built enough roads just in the United States to encircle the equator twice. And we went from using landlines and postage stamps for communication to the internet revolution and computers you carry around in your pocket, and 6 billion connected people with cell phones. So, you know, these are things we actually can do in terms of the mechanics. Likewise, transportation energy system, we've already got the cars out there on the road. Battery technology is coming along to the extent where it's possible. Airplanes. Did you know the U.S. Navy ran their entire Pacific fleet on a training exercise on renewable fuels? And what they flew their airplanes on was algal-based and cooking oil-based biofuels, including jets, fighter jets. So we know how to do this. The cost has to come down. But again, that's the top billion that can do that pretty easily. Each person in the top billion, paying by tax or whatever, $700 per year would solve the problem. Okay? My plane ticket here probably costs more than $700. That would reduce carbon emissions to 0 by 2100 and also provide clean energy access to the bottom 3 billion. Now, I should point out that these numbers that I've been showing you are courtesy of my colleague Vrabdran Ramanathan, who's at UC San Diego and a fairly well-known climate scientist. Okay, so the developing world's a whole different set of problems. You know, we have to bring energy use up in those places, but in a way that doesn't commit us to more greenhouse gases. And turns out that's already being done too, by leapfrogging. You know, it's easier in places like Nepal to not have this huge electricity grid. This is a hospital that's at the base of Mount Everest. It's a state-of-the-art hospital. It's run entirely on solar and micro hydropower. 100% carbon neutral and doesn't have to be connected to the grid. So again, we know how to do this stuff. Why don't we do it? Well, a lot of it comes down to money. A lot of it's going to take some top-down action and international agreement. And this is a realm, in fact, that scientists have a big role to play in. I'm going to give you just a couple of examples here, and then we'll wind it up. But this is China's top climate official. This is California's Governor Jerry Brown. And they, through a variety of negotiations, arrived at this memorandum of understanding between the state of California and China, first time China has ever made an agreement with a subnational, to reduce greenhouse gases in their respective domains by a certain amount, to collaborate on developing green energy technology. And it turns out that Governor Brown has initiated and made these international agreements and gotten commitments from a variety of subnationals and even national governments. Now, how did that come about? Well, I love the fact here that he's making an announcement about climate change and using as the backdrop extinct animals, and he actually made the point, do we want to see this happen? But the way this all came about, actually, or at least contributed to it, was a few years ago, 2013, I think, I was part of a group that published what we thought was going to be another scientific study in Nature that a few scientists would read, but probably nobody else, called Approaching a Tipping Point in Earth's Biosphere, and it caught a lot of attention. And one of the people's attention who it caught was Governor Brown. I was out running with my dog one day, right after this came out, and my cell phone rang, and I picked it up, you know, panting, and the voice on the other end of the line said, "Can you talk to Governor Brown right now?" I said, "Sure." I mean, cold call. He had caught wind of this and had a long discussion, and basically, over a few subsequent discussions, these are the questions that he asked. You know, he says, "Why aren't you scientists shouting this out? How come you're only talking to each other?" And, you know, I said, "I thought we were shouting it out." And he said, "Nope, if you were shouting it out, I'd know about it." You know, where are the young people? how do you counter these climate deniers? And then he issued the challenge, can the scientific community come up with some sort of unified voice that I can use? Am I out of time? Okay, well, all right. And we did, and that's it, okay? And I'll just quickly finish up. This thing actually covers a host of issues, not just climate change, although the governor uses it primarily for climate change. But the point is, he uses this and other such documents to build some huge international agreements that are really helpful, one of which is this Under 2 MOU, which subnationals and some nations sign on to hold greenhouse gas emissions over the next few decades to what it will take to keep the world below 2 degrees C. Right now, the groups that have signed on to that collectively rank third behind China and the USA in emissions. So these kinds of things make a difference, and they originate from science. There's another one that I'll skip over. Last thing that scientists have a role in is not only with the top down, but also talking to people outside of academia, okay? And it's really important to convey what the scientific realities are, because people, surprisingly, trust scientists more than they trust their own family on many issues. There have been polls done on this, and the most trusted source of information for things like climate change are scientists. 74% of the public trust scientists, 64% of the public trust their own family, and then it goes down from there. Okay, so we do have a role to play, have to communicate the solutions. Nobody wants to hear about the problems. And we have to not just preach, but facilitate dialogue. And you have to target this group in the middle. So people have done studies that show that in any distribution of constituencies that has to do with motivating social change, you always have about 20% who are in it for themselves. You have about 20% who want to work for the common good. But then there's a 60% in the middle that haven't really made up their mind one way or the other. So our task as scientists is to help that middle group make up their mind. And I'll just close by saying, we know we've got a problem with biodiversity crisis. Even the most conservative analyses that I just showed you tell us that. We also know that as scientists, we have a critical role to play in stopping it, both by doing the good science, but the scientific paper really is just the first step. We have to step outside, as Rodrigo pointed out this morning. And I'll just leave you with a thought that, you know, the 1960s, all of a sudden, news started coming out that 1 billion people were going to starve to death if we didn't do agriculture differently. Through putting together the same kinds of collective action that we need to solve climate change, that we need to solve the food problems, the ecosystem services problems, same sets of ideas but different issues. 20 years later, that problem was solved, you know, largely due to individuals taking collective action in their own realms. And of course, the real person known for that is Norman Borlaug, who was a scientist. So that's our job. Save the world. Thank you.